Friday. I have it over sign test and t-test data file.
There's just the one data file, right?
Yes, leaves.csv. Just the one. Just the one data file. When you import it, you should have 2 columns in it, two variables. It's open. So once you start that, it is 15 minutes starts there. It is a series. You can't go back to previous ones because it'll kind of build on. I don't want you to like say, oh crap, I see the output. That's what it should be. You are done. You will start working. Yep. And then hit file, save as. Bottom here. .rm.
Yeah. Chlorophyll concentration. And I skip that in the RMD file. So quiz 15 minutes. Check. Test description says 5 minutes. It's 15 minutes. Oh, okay. Yeah, just close out of that. Well, as you said. Yep. What is the function where we have the brackets? It was like something over n minus.
Okay. That what?
You know that long function that we wrote out on the board?
I don't know.
It's probably not gonna be.
round it as you should. And then I think I have it set up so, yeah, just round it as you should, based on our round.
Oh, that would be bootstrap.
Okay, yeah, we don't need those. bootstrapped function. Forgot about that. Get it? All right, I think we got through it. All right, so exam schedule for Monday. What we're gonna do is hold off until Wednesday. And the way what we'll do on Wednesday is we'll come in and do the closed book at 11. All right. And what I will do on that Wednesday is make the application part go live. All right. I'll have it go live first thing in the morning. And then you have all day Wednesday to finish it, to do it and get it submitted. There's a class in here at 2 o'clock. I think it's 2 to 4 maybe. So you can't come in at that time, but I'll be available that morning to answer questions and also through email if you get errors and stuff. All right. Because what I want you to do is kind of, we can see this. We've got these 2 homework, these 2 quizzes. I want you to kind of be able to go back and redo these quizzes, because if you can't do the quiz, if you can't do the stuff on the quiz, it's going to be hard to do it on the actual exam. So Wednesday we'll do the closed book part. All right. So what about this quiz? I've got my functions, I've got my data, and really there's just been about 2 things that, maybe 3 things that we're doing. So if we looked at our data, we have back here, we have 2 variables, length and chlor. And the problem talks about we measured length of the leaf, some leaves, and we also measured chlorophyll concentration of the leaves. Right? So for the t-test, we have the data, we have a vector, and we ask, I don't know what it was, 300, 400, something like that. We don't have to calculate our t observed, because since we have the vector, R will do it for us. So we can specify leaves $length, and then tell it what we're testing against, what average we're testing against. So maybe it's 400. And then we have to have our alternative. And I can't remember if it was 2-sided, greater or less, or something like that. Maybe it was less than that. So once I just issue that command, we look at the output, and it tells us everything that we need to know. And again, I don't know what the mu was. I don't know if it was 1-sided or 2-sided, but we do that, and we have our t-test, our test statistic, we have our p-value, and then we just look at that p-value for the interpretation. We also, I think, may have had to check assumptions. Sign test, same thing. We have the vector, so it's just issuing the command and specifying what we're testing it against. Maybe that was 400. Maybe that was like 15 or something like that. I think the median may have been 400. And I don't know if it was less or greater. Can't remember. But something like that. And then we get our p-value, and that's what we look at. What do we do with the bootstrapped? Well, again, we have bootstrap means. You can do leaves, chloro, 10,000 iterations, and the default is 95%, so we can do that. And then we can always check it a couple times just to confirm that we're getting the similar answers. And remember, with our bootstrapping, or even just with our confidence intervals, we would conclude that our mean is not equal to any value that is not captured by that range. So that's why I did it a couple times. If we had 177.6, well, that's not in this range. So we would conclude that our sample mean is not equal to 177.6. But if we run this a couple times, it's a possibility that we would catch it, like here. So if we're on like the edge, yeah, run it several times. It doesn't take too long. Let's check to see if it's getting captured or not. But if you have something like 170, it doesn't matter. We're so far in this range that the only numbers that are changing are these two, and they're only changing by decimals, right? So remember that's what we're going to do. What we'll do on Monday is I'll go ahead and clear the attempts on the quiz on these last two quizzes. So then on Monday in lab, you can do a reattempt to see, hey, are we getting it? Are we getting these tests done and everything? All right. So it's our quiz. We're gonna go over fish length, but I think some of you probably Usually it's open as long as the building's open. It's open as long as the building's open. Usually I make it 11:30. Yeah. So just know that don't wait until 11:25 to knit it and you get errors, because I might not be able to respond. So that's the case. If you're in that crunch, you can always submit the RMD file, because I can see where the mistakes are. So I want to point out some stuff. So things that we're getting to. After we do the Anova, we typically kind of do a rehash of our tests and our Anovas. So I have these PDFs created that kind of go through our flow chart of what variables do we have, what are their type, and then what are the options for our analysis. So you can start looking at these to see, okay, we have one variable. We've been working with discrete or continuous variables, all right? And our figures that we could use would be a histogram to show those. And then the tests that are available to us include the z-test, the t-test, the sign test. Shapiro-Wilk is a one-variable test, that tests for normality. QQ plots, that's our assessment. We can do bootstrap 95% confidence intervals. This is kind of saying this is what's available, and then it's up to you to know what is the z-test testing. When would we use a t-test or a sign test and so forth. We have two variables. What we're working on right here are these. So we have one categorical and one continuous. Box plots tend to be what we would use in R. And then we have all these tests that we can run. A two-sample t-test. So a t-test, Welch's t-test, Anova, Welch's Anova, Kruskal-Wallis, Brown-Forsythe, Fligner-Colleen, Tukey HFC, Dunnett's, permutational Anova, permutational t-test. We can run all these tests with data like this. It would be up to you then to recognize when do we use each one. All right? So that's available to you. And then what we're at right now is with the Anova flowchart. So this is also posted. Get rid of that.
Wait, where is it?
There it is. Lecture just below assumptions are violated.
Okay.
So I've got this test flow. And this is kind of what we're doing. This is what you're supposed to do with your fish length. So we know what we want to do. We've gone through that first flow chart to say, all right, we're testing for means. We have one categorical. We have one measurement variable. That categorical variable has more than two groups. So Anova is what we want to target because we want to compare our means. So once we've made that choice to run an Anova, now first step we do is test for normality within each group. And we're going to use our QQ plots for that. All right. If it's a yes, which is what we're on, all right, then our next question is, are the data homoscedastic? So do we have equal variances? And for that, we're going to run our Brown-Forsythe test. Or, yeah, we're going to run our Brown-Forsythe test because Fligner-Killeen shows up here. So if we don't have normal data, we run our Fligner-Killeen test. Or if we're questionable, we can run our Fligner-Killeen test. Right now, we're dealing with assumptions are met. So then we check equal variances. Our choice, we're either have equal variances or we don't. If we do, then we ask the question, are the means different? And we actually perform our Anova. If we violate this equal variance assumption, then we're going to run Welch's Anova to answer the question, are the means different? All right, so we're at here, we do our Anova. If we get a significant p-value, if we get a non-significant p-value greater than 0.05, it means the means are not different, and we stop. That's it. But if we do find a difference in mean, the p-value is less than 0.05, then we go to that last step, which is which ones are different, which means are different. And then that's where we run our post hoc test. So from now until the end of the semester, we're going to cover the rest of these. What happens when we enter these nodes? Where do we go? How do we do the test? And so forth. So I'm going to present this now because I think it might be useful on the exam, and you say, why would that be useful on the exam? Well, because we started with this. We started with these one sample tests, and then we're currently at our two sample tests and ANOVAs. And in that process of getting to the ANOVAs and doing the ANOVAs, we've introduced quite a few tests. So on exam 3 and on the final exam, we not only have like definitions and like questions like what are the assumptions of this test, or what's the null hypothesis of this test, what is it testing? We have questions like that, but then we also have what I would call closed book application questions, which is I give you the scenario, I say this is our experiment, these are the data that we collected, this is the question that I want to answer. What test do we run? So that I consider kind of closed book. Okay, so you could say we have a lot of tests. We don't. I mean, 10, 15 tests maybe, at best. And I think it's pretty easy to kind of remember what tests we're running because we're just doing it in such a progression. Final is comprehensive, so it'll cover everything that we have. And that's why I put also display. What display should we produce? What display should we produce? What test? Which of these tests have one-sided and two-sided tests? Which of them don't? So like Anova, the one-sided, two-sided doesn't really apply. Right? Same thing with like your Brown-Forsythe, Fligner-Killeen. Two-tailed, one-tailed doesn't really apply. All right. But if we have two sample tests, a two sample t-test or a one sample t-test, we could say, is one larger than the other? And that sets up our one-tailed test. All right, so that was under a lecture, so you can check those flowcharts out. And I think it'll be good to kind of postpone the test for a day. That'll give us time to kind of get through this fish length, review, answer any questions, and kind of redo these quizzes just to kind of check to see what's our progress, how are we doing it, or starting to understand how to get this run in R and so forth. All right, so fish length. We measure fish, 5 different lakes. We ask the question, are the mean lengths different? So first thing we do with this is we look at our data. Again, big part of looking at our data is just to confirm we didn't have any typos. All right, so I looked at the data. I just did a summary of my data frame, which is useful because it's going to give me counts. So we have 55 samples from Big Bear, 55 fish. We have 50 fish from deer. We have 45 from green. We have 51 from mallard and 53 from ram's head. So this is pretty good because it gives all 5 of our names, all 5 of our lakes. But know that if we have, let's say, 7, 8, 9 different groups, R will list like the first 4 or 5 and then put other for all of the rest. Utility, so summary is going to be a little bit limited. But then for our measurement variables, it gives us this summary, which is minimum value, maximum value, median, mean, and third quartile. So what, this fish line?
Yeah,
What did we measure? Those look off. The Y's look off. So if you made a graph, did it look like this with the Y-axis? Right? Huh. Okay, presentation. What did we do? Oh yeah. We'll assume that this is feet. Decimals in feet. Right. So I'm going to do a plot. So the summary doesn't really give us ideas about the averages. I'm going to look at the plot, and just right now, I don't see any point that seems outrageous, right? I don't have all of my boxes right down here and then, points that are 10, 15, 20 units above it. All right, they all line up pretty good, so okay, that's good. I look at the lines, I look at the medians in these box plots, and looking across it, if all the means are equal, then we should all be lined up. We're pretty close in a horizontal line. We're not. So when I run the Anova, if we can run the Anova, I'm not going to be surprised if I get a p-value that's less than 0.05. And then when I do a post hoc test, if I have to do a post hoc test, I'm not going to be surprised to find a difference in our 2 extreme values, the largest and the smallest. They look different. And actually, when you look at the boxes, the interquartile ranges, they don't overlap. So I'm kind of starting to suspect, okay, deer in this last one, which is ram's head. Ram's head might be different. So I think if I widen this, yep, there it is, ram's head. So I'm not going to be surprised if those are different. I'm also not going to be surprised if I don't find a difference between Big Bear, green, and mallard, because those medians seem to be captured by the interquartile ranges of the other ones. But again, this is medians and interquartile ranges. That's not what we're interested in. We're interested in means. So I'm just using this to kind of get an idea of what to expect. Do I expect violations of normality? Not really. All of our lines seem to line up right inside of the interquartile range. I don't see any major skew in our whiskers, so that's good. All right. What about equal variances? All of our whiskers and all of our boxes appear to be similar in size. This one might be a little bit smaller. This one's smaller, and these 2 are larger. But are we going to detect a violation? I don't know, probably not. So I looked at the data, have a nice idea, and now we want to start pursuing this Anova. So remember, our null hypothesis is that all means are equal. Our alternate is that at least one mean is different. So if I look at my flow chart, it says we've got this Anova. The first thing we check is normality. So I check normality with my QQ plots. Now these are all pretty small points. These are all pretty small points. But I can see that for mallard, it looks like all of the points are lined up inside that, inside the envelope. Ram's head, same. Green, the same. Deer, the same. And about Big Bear's the only one where there might be some points falling outside. If it was just a single variable, if we were doing, let's say, a 1-sample t-test on Big Bear only, I might take some corrective actions. I might say, let's be cautious and not assume that this is normally distributed. But Since this is forming part of a larger data set and we have 5 groups and 4 of them look real good, I'm going to conclude that Big Bear is probably also pretty good. So that we are normally distributed. Questions on that interpretation? Would you agree with that? It's probably normally distributed. So data appear to be normally distributed within each group. So our next part on our flow chart is that we have to check our equal variance assumption. So we're normally distributed. We have our so our option to check that equal variance assumption is Brown-Forsythe or Fligner-Colleen. We're going to run Brown-Forsythe because our data appeared normally distributed. So I run the Levine test with the center equals median. That's how we run our Brown-Forsythe test, and I get this output. Now that some of these values are useful, the F statistic is useful, the degrees of freedom, both degrees of freedom are useful. Or 184.89, those are all useful. But what I'm going to look at first is this value, this p-value. So our null hypothesis for this test, variances are equal. Do we reject that null hypothesis? No, p-value is greater than 0.05, so we don't reject it. We conclude that our variances appear to be equal. So we're normally distributed, and we have equal variances. It means our assumptions are met. Let's go ahead and proceed with the Anova. So I create my model. I called it fish mod. Right? And we're doing a linear model where we're trying to predict length as a function of lake. So that's kind of what we can talk about a prediction. We're predicting length as a function of lake using fish data. Create that model, and then I do the Anova table. And I use the capital A. If you use the lowercase a, you'll get the same. You'll get a similar output. Lowercase a looks like that. Uppercase a looks like that. So they're similar. Not identical, but they're similar. All right? The lowercase a gives the mean squared values and the sum of the mean square and sum of squares. The capital does not give the mean square. It just gives sum of squares, degrees of freedom, and F. But the p-value is the same. So again, we have useful information in this output table, but the one that we focus on is this value. So 4.16 e to the negative 11. What's our conclusion? We know a difference exists, right? So our null hypothesis was that all the means are equal. We get a p-value that's less than 0.05. So we conclude, yeah, the means are different. So based on Anova, we know that at least one mean is different from the rest, but we don't know which one. So our final step with this analysis is to figure out which one's different, and we're going to use two keys. We're not comparing anything to a control. We're just comparing all of the lakes to see which of these lakes have a difference in mean. So we already have our model. That's what we want, fish mod. All right, and to run two keys, we're going to use 2-key HSD of the AOV of the fish mod. So that entire command with your appropriate model. I don't know what you called your model. I called mine fish mod. We get this. We get this big table. So now here's where the fun begins. Because we look at this table and we're looking at every row that has a p-value less than 0.05. We're looking at all of these. So Deer and Big Bear has a p-value less than 0.05. I know that the means are different between Deer and Big Bear. I go down to the next one, Ram's Head and Big Bear. Those means are different. Green Deer, those means are different. Mallard and Deer, that's different. Ram's Head and Deer, that's different. And Ram's Head and Mallard, that's different. So we could go through and just list, okay, these are the means, these are the lakes that differ in their means, and just list them. But if someone's reading that, they're going to be really confused. they're going to get confused because they're just seeing all of this and they're going to think, how does this all fit together? Where does this all go together? So probably an easier way is, instead of listing out every single one that's different, is inspect the data set to see, do we form groups? It's one thing to say, yeah, all means are different from each other. That's easy. Or no, only this one is different from the rest. That's easy. But how do we handle something like this? Well, my recommendation is always to start with the averages. Figure out the averages that we're comparing. So these are the averages. I use the aggregate function to get them. And then from the averages, I am going to rank our lakes from smallest to largest. So Ram's Head had the smallest mean, 0.68. Green had the next smallest. And then we had Mallard and Big Bear and Deer. All right, so I have them ranked smallest to largest. Now what I'm going to do is go make a progression. Make a progression and do lakes that are next to each other. So I'm going to look at Ram's Head and Green. Ram's Head and Green is this row. That p-value is greater than 0.05. So what I'm going to do, I'm going to use dashes. I'm going to draw a line over Ram's Head and Green. And that's telling me that these two lakes are similar. P adjusted?
Yeah.
Yep, that's our p-value. It's greater than 0.05, so there's no difference in mean. Right. So then I'm going to go to the next one. So Ram's Head and Green are similar. I want to see, is Ram's Head and Mallard similar? So I go to Ram's Head and Mallard. No, they're not similar. Now we have a p-value less than 0.05, so my line that I've started to draw stops. That line stops. So, yep. So that's going to stop. So I've got Ram's Head and Green. Now I go to the next lake. I don't have to compare Ram's Head to Big Bear or Deer. I don't have to do that because since I've ranked them in order, once we hit Mallard, any lake that has a larger value than Mallard is by consequence going to be different than Ram's Head. And you see that in the table. You see that in the P table. So we found our first break. So next up is Green. Is Green and Mallard different? So I go to Green and Mallard. There's the row. P-values greater than 0.05. They're not different. So I'm going to go to Green and Mallard. And I'm going to start doing a line over those two. There's no difference. And then I'm going to go to Green and Big Bear. So that's our next step. Green and Big Bear. P-values greater than 0.05. They're not different. So I'm going to continue that line across to Big Bear. So now we know Green is not different from Big Bear. And if Green and Big Bear are not different, the Mallard's not different from either of these. Because again, Green is actually smaller than Mallard. Mallard and Big Bear are closer together. So our last one is to go to Green and Deer. Where is Green and Deer? There it is, Green and Deer. Small p-value. So my line stops. Now, I could go to Mallard and look at Deer, but I'm actually going to do Big Bear. I'm going to do the closest one to Deer and see, is there a difference? Big Bear and Deer, they're different. So I'm going to go down to Deer and just put a line over it. And what that tells me now is we've basically formed three groups. Ram's Head and Green form a group. Their means are similar. Green, Mallard, and Big Bear, they form a group. Their means are similar. Deer is off by itself. That's the one that is different. So in our text now, instead of listing, okay, Ram's Head and Mallard's different, Ram's Head and Big Bear's different, Ram's Head and Deer's different. We don't have to list all of them. We could say our data form two groups. Ram's Head and Green are similar, Green, Mallard, and Big Bear are similar, Deer is larger than the rest. So what we'll do is I have a figure that translates this part to a figure using subscripts. So we'll talk about that on Monday. And I'll also put up the write-up that I did. All right. So this will also give you some time since we shifted things. I have some homework. Let's see if it's up. Oh yeah. It is. Because it wasn't submitted. So homework 11, Anova. This is all practice. Because you're going to be doing the Anova on the ANOVAs on the exam. So our exam covers one sample test up through Anova. All assumptions are met. So go through and check your assumptions, check your normality, check your equal variances. My guess is that we did violate normality or violate equal variances because this was kind of like a ANOVA stuff. But what we can do is kind of ignore that and just kind of get through, do the steps to get to ANOVA. All right? I don't have a date. It'll probably be due when we're done, when we finish all of ANOVA and all of the assumptions violation.
Will we have lab?
Technically, yes. Technically, yes. That could be a good time where lab is working on this to hand it. I think that's what I did last time.
Both of the other ones don't have lab.
No, well, ecology only has, well, we have Wednesday and Thursday labs, so those can't be. But yeah, usually that Thursday, that lab on Thanksgiving week, that Monday, I make that as a homework or project. So, yeah, this is probably going to be due during Thanksgiving because I think we'll have all of our assumptions and stuff. All right. All right. So kind of start reviewing, and yeah, as I said, I'm gonna clear out the attempts on those quizzes. So on Monday you can retake them to kind of again check and assess your progress. How well am I doing on those? I'm actually doing these analyses. Sorry for running late.